So the final, it will be Thursday. Okay, the first day of the final week. Okay, don't forget that because there is no makeup. It's gonna be too late because it's the first day. And then I have to post everything for those who are graduating. So the first day. I forgot the time, but I know it's the first day. Okay, so don't forget. And I will post a practice test, and it won't count. Okay, you don't have to worry about the grade. Okay. What else? Nothing. So let's review a few things here. So this is my slides, big ideas. And you see, I fixed the typo. So for the final, you have one problem on the transformer. It's very easy to understand. You see here, you go from 10 loops to 40 loops. So number of loops is multiplied by 4. So it means it's a step up transformer. So it means the voltage will be multiplied by 4. But because energy has to be conserved, you see, the current will be divided by 4. So if you have a step-up transformer, the voltage increases, but the current decreases, such as when you multiply the power, which is energy consumed or produced per second. The power is the voltage times the current. So here it's going to be 12 watts. Input is 12 watt, output is 12 watt. Okay, so we already discussed that a lot. So here you connect that to a AC power supply. Okay, so the magnetic field will be constrained. Okay, inside this soft iron donut, kind of. Okay, so the magnetic field is going to change. Okay, it's going to expand, collapse. Okay, and that's why here you're going to have an induced EMF, and it will be also AC, and you can step up the voltage or step down the voltage. So here it's a step up voltage. Okay, we already discussed that. I forgot to show you this app here. You see that nothing happens there, nothing is induced. So here you have an electromagnet. You can use your right hand, so it's a nice review. So what you are seeing here is electrons. So it means the positive charge are moving in the opposite direction. So that means that side here will be north, this side here will be south. Okay, so the magnetic field lines here are poking through this invisible membrane, but they are not changing with time. Okay, so the number of field lines poking through this area is not changing with time, so you are not inducing anything. However, if instead of having a DC here, I have an AC, so you see here the number of field lines are changing with time because magnetic field expand, collapse, expand, collapse. So now you are inducing a current and an EMF. I can put a voltmeter and that will be always AC. Okay, it's not much. If I want more, I can increase the number of loops here. Okay, so I get a little bit more voltage, and I can also increase the area, and I get a little bit more voltage. Okay, is that clear? So that's how transformers work. Okay, and what else did we talk about? We talk about Lenz law. So the pop quiz of today is not going to be that intuitive. It will be about Lenz law. So remember that the current induced will always oppose whatever gave rise to it. So in that case, for example, you bring the magnet toward. So it means the magnetic field is gonna, the number of field lines, okay, is gonna increase. Okay, so you go in. So the current here is gonna flow in such a way, okay, that it's gonna show the north here. So that side here will be north. So that way, it's going to say, slow down, slow down. You know, I don't want you. Okay? No, 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 no. Don't get near me. And then if you change your mind, you're going to pull the magnet away. So the number of field lines poking through this area is going to decrease. So now the current is going to flow in the opposite direction. You see, you use your right hand. It's going to flow this way to expose the south face here. So now here it will be south and here it will be north, in such a way that when you try to pull the magnet away, it's also going to be hard. It's going to be trying to say, no, 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 don't go, I changed my mind. Okay, so if the magnetic field increases, it's going to try to decrease it. And if the magnetic field decreases, it's going to try to increase it. So that's called Lenz law. And for example, here you see you have a plate, so conductive plate. It's made of copper, and it's like a pendulum. Okay, so when the plate is going inside the magnetic field, you will induce a current, which is called eddy current, and it will oppose whatever gave rise to it, so it will stop it. Okay, so this is called a magnetic break. Now, if you have an opening there, of course, the current cannot flow, so it won't work. Okay, so that's how it works, a magnetic break. Okay, so we discussed that, and I forgot also to show you a video. So it's from the channel, YouTube channel Veritasium. And it's
I like
also
to
about
think of Lenz's
Lenz's
law as the no you.
So you see here inside, you have a very strong electromagnet. So it's an electromagnet that you connect to a AC power supply. So this electromagnet is going to produce a magnetic field that will change with time. So the magnetic field is going to expand, collapse, expand, collapse. So it's going to induce current inside this plate. Okay, they are called eddy current. And the current here is going to flow in such a way that it will oppose the magnetic field that gave rise to it. Okay, so now if it tries,
Don't law, because whatever you try to do, nature acts to oppose you.
There you go.
If the plate is falling, eddy currents are induced to slow its descent. But if you try to pick up the plate,
you can't.
nature also says, no you don't. In this case, a south magnetic pole is induced under the plate, attracting it back to the magnet.
They don't know if I'm weak.
Did you see what's happening here? Okay, you're gonna have an induced current. Okay, that induced current is gonna flow in such a way that it's gonna expose here a south face, and the electromagnet, this is a north face. So I don't think you need to connect it to a AC power supply. Any power supply will work because you are not moving the electromagnet, you are not moving the magnetic field. The magnetic field is not changing, but you are moving the plate. So that will be enough.
They don't know if I'm weak or if this is actually insanely difficult. Oh my goodness.
You're strong like bull.
Oh.
No matter how hard I tried to push the plate down, it just wouldn't go very fast. Because even if I could speed it up a little bit, that would increase the rate of change of flux, and hence the induced currents and their associated magnetic field.
That is ridiculous.
Yeah. We tried a number of other conductive but non-ferromagnetic objects around the magnet, like this thick cylinder of aluminum. Drop it straight on the magnet, and nature says, no you don't. Try to roll it across the top? No you don't.
It just refuses to roll.
We wrapped up a volleyball in aluminum foil and passed it across the magnet. Or dropped it straight in. Again, the changing magnetic flux induces eddy currents that produce their own magnetic field to oppose the original change in flux. I like to think of Lenz's law as the no you don't.
Okay, so no you don't, okay, for the pop quiz? That's actually a better way to remember. No you don't, okay? That's Lenz's law. So eddy current will always oppose whatever gave rise to it. So that's from the YouTube channel Veratisium. Okay, what else I forgot to show you? At the end, so remember for the final, at the end of these units, 3.1, 3.2, 3.3, you have equations here. Those equations come from the book Johnson and Cudnell, and you can print them out for the final. I'm not going to have extra for you, so just don't forget to do it. You even have the explanation here, okay? So this is called the motional EMF, okay? We already talked about that. So if you have, for example, a conductor, like a loop, and you move the loop through a region with magnetic field, you're going to induce an EMF that will be given by this equation. That will be the equation for the magnetic flux, okay? And that's the equation for the EMF induced if there is a change in the number of magnetic field lines poking through the membrane attached to your loop. Okay, so we already talked about that. That will be also in the final. There is one question about that. That's AC generator. So you take a loop and you rotate the loop at a given frequency. So in that case will be 60 revolution per second inside the uniform magnetic field, and it will induce EMF that will follow a sine wave, okay? And that expression here, that's the one you want to remember, will be equals to the peak EMF. So in our case here, the peak EMF is about 170 volt AC. Okay, so it depends on the number of loops of the coil rotating in your uniform magnetic field. It depends on the area of the coil rotating in your magnetic field. It will depend on the magnetic field that is not changing, only the loop is spinning. Okay, and it depends on the speed of rotation. Okay, so to produce electricity from here, the speed is about 60, it's a 60 revolution per second. That's why the frequency is going to be 60 hertz. Okay, so this you don't have to worry about that. And this one says that if you have a solenoid, okay, connected to a power supply, solenoid like a coil, okay, and you turn on, so you close the circuit, okay, so you connect it to a power supply, you close the switch, there will be a back EMF. So it means that it will take time for the magnetic field to expand. Okay, it will oppose the building up of the magnetic field or the building up of the current. That will be the EMF here. So that will be this one, this equation here. But you don't have to worry about that. But just if you want to understand, if you want, I can explain more in details at the end of the class. But for the final, you don't have to worry about this equation. You just want to worry about those equations here. Also, at the end of 3.1, 3.2, you also have equations. You can print them out. Is that clear? Okay, cool. So Lenz law. So you're gonna have something like this. Okay. So a magnet comes here toward the coil here. So you have a coil. It's connected to a galvanometer. So it's to measure the current. So it's not a power supply. There is no current flowing. And you bring the magnet toward the coil. So no, you don't. So the current induced is going to flow in such a way that what's going to be the phase here? South or north? No, you don't. No. If you make it no, you are yes, yes you do. You don't want yes you do. You want no you don't. So you bring the south. So this one will become a south because hey, welcome back. It wants you're right. Never. So it's gonna be repelled, right? So no you don't. It's not yes you do. It's no you don't, right? So it's gonna flow this way. Do you agree? Right? So now you have a south here and it will repel the south. Is that clear? So the current is gonna flow in this direction. Okay? Yes, in these directions from X to Y. Okay, so you're gonna have a equation like this. So here it's flowing from X to Y and then in the circuit. Is that clear? Now if you want to pull the magnet away, what is gonna happen? No, you don't. So it's gonna flow in the opposite direction, and that face here will become a north. Very good. Okay. So remember your right hand. This is the current flowing, and the thumb is the north. Because I like that. No, you don't. Okay, that's a good way to remember. Likewise, which way is flowing in that case? Is it 1, 3, 4, or 2? So going in? No, you don't. 1, very good. 1, very good. Do you all agree? Right? No, you don't. That will become a no. No, you don't. No, 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 no. You come in, and this is a north. So it's gonna 2, 2. Okay, 2 because that way that will be the north, and north will repel each other. And if you try to pull it away, it's gonna be 1. Okay, because now I say don't go. I change my mind. Stay. So that's how Lenz law works. So here you have a ring, and it's falling. It's falling, and it's going through this region with a magnetic field. So when it's gonna enter inside the magnetic field, which way it's gonna flow? No, you don't. Right? So the magnetic field is going where? In the screen or towards you? In the screen. And they say, no, 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 no. You're increasing the number of lines through the area. I don't like that. I'm gonna fight you. So it's gonna flow. Which way? Counterclockwise. Counterclockwise because it says I'm gonna fight. I don't want you. Magnetic field is in the screen, so it's gonna flow counterclockwise, so it's gonna fight against. Is that clear? So when it's falling through this area, nothing happens because the number of lines poking through this membrane, invisible membrane, is not changing. So when it's falling from here, inside here, nothing happens. Only when it's gonna exit this region, you see the number of feed lines poking through this area is gonna decrease, and it doesn't like it, right? It said, no, you don't. I don't want you to decrease. Now I'm gonna help you. So it's gonna flow clockwise. Do you see how it works? So if the number of lines are increasing, they say, no, you don't. It will make it decrease. And if it's decreasing, no, you don't. It's going to make it increase again. Okay? So that's how it works. If you change the area, also it's going to induce EMF. What about here? Is a EMF induced here from here to there? No, very good. Okay, because the number of feed lines poking through the invisible membrane attached to the conductor is not changing. You need to have a change in the number of feed lines poking through this membrane, imaginary membrane, attached to your loop. Is that clear? So likewise here, if you bring the magnet toward, it's gonna flow this way to opposite, right? If you move away, it's gonna move in the opposite direction to say, no, you don't, come back, okay? I changed my mind. So that's how Lenz law works. Yes, yes, because if there is a if it's something has to change. So if the area is changing, so yes, there will be an induced EMF. So if you go back to here, so you have a different way to induce an EMF, and here you can change the area. Okay, so here you have more feed lines poking through that membrane, and here you have less feed line. Even if you're doing this, that we did that as a problem, you see the area that poked through by the magnetic field is increasing. So that's why you have an EMF. Okay? Is that clear? Okay, so up to a new unit. Oof, we made it. That was a challenging problem. Not very challenging for the math, but it's challenging for the concept. So we survived. That's good. So about electromagnetic spectrum, okay, and we're going to talk about light because I know for the MCAT, I think the last exam they ask about light. So let's go over light. So this is the electromagnetic spectrum. Okay, and the first thing to know is that all this part of the electromagnetic spectrum, they all move at the same speed. So from high energy to low energy, from high frequency to low frequency, from low wavelength to large wavelength. You see, you go from gamma rays, X-rays, UV, visible light, infrared, microwave, radio wave, long radio wave. All of them, they travel at the speed of light. So they all have the same speed. So if I try to trick you and I say, okay, gamma rays, obviously they have more energy because you know that you don't want to be exposed to gamma rays, right? Too much. So they're gonna move faster. No. Don't be tricked. They all move at the same speed. That will be the speed of light. So this here, that will be very high energy. So could be dangerous, kind of dangerous, safe. So high energy here, they all have a high frequency. So the frequency is going to be very high. So that means oscillating faster, and that will be low frequency. So here you have the wavelength. So we're going to talk about that, so don't worry. But gamma rays, not very safe. X-rays, UV, visible, and everything here is very safe. So that will be called the electromagnetic spectrum. So why is it called an electromagnetic spectrum? Because it's made of an electric field and a magnetic field. So remember, when you have an electric field, okay, an electric field like current, it will induce a magnetic field. But a magnetic field can induce an electric field. Do you agree? That's what we have learned. So how does an electromagnetic wave works? Okay, you're gonna have I will go in more details, but you're gonna have an electric field that will shake, okay, that will induce a magnetic field that will change with time, that will induce an electric field, that will induce a magnetic field, that will induce an electric field, that will induce a magnetic field, that will induce a electric field, that will induce a, and so forth and so on. So it's auto-generating itself, right? So that's how an electromagnetic wave works. So all the Wi-Fi that we have here, when you are using your phone, or the electromagnetic wave, the signals that are sent, it's all made of an electric field and a magnetic field, an electric field and a magnetic field. So that's why I told you, when those waves go through you, when the magnetic field goes through you and it's changing with time, it does induce current. Okay, so the current induced will be very small, of course, so hopefully it will be safe, but it does do stuff, right? Even though you cannot see it with your eyes. Okay, so let's review waves first, right? So you have a wave. Now, the distance between the crest, it's called the wavelength. Okay, so if you take a picture of a wave at a given time, like you are looking at a pond, for example, you're going to see a water wave moving. It's going to carry energy with it. And from the above, okay, you're going to see crest through crest. That distance here is called the wavelength. Now, if you are at a given time, it's going to go down, up, down, up. Okay, so the time it takes to go up, down, up, it's called the period. So I'm going to show you an app. I'm going to make a water wave. Boom, boom, boom. So you see, that will be a crest and that will be a throw. The distance between two crests is called the wavelength. Now, if you are looking at a position here, you see that position here, it's going to be a throw, a crest, a throw, a crest, a throw, right? The time it takes to go from crest to throw back to crest, that's what we call the period. How many cycles per second? It's going to be the frequency. So I can increase the frequency here from the source. So I'm going to increase the frequency. What's happening to the wavelength? So the wavelength will be crest to crest. Did it increase or decrease? Decrease. Okay, so when the frequency increases, the wavelength decreases. Do you agree? So here I'm going to decrease the frequency. Boom, boom. Yeah. Now, do you see the wavelength? Okay, did it decrease or increase? Decrease, right? So what's the wavelength? Again, it's the distance between crest, or it's the distance between throw. That will be the wavelength. So that means you take a picture at a given time, take a snapshot, bling, and you see the distance between crest and crest, that will be the wavelength. Now, if you stay at one given position, the time it takes to go crest, throw, crest, that will be the period. Yes.
So for frequency and wavelength, do you maybe think that they are inversely proportional?
Yes, absolutely. They are very good question. They are inversely proportional. Why? 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 Because yes, they are inversely proportional. That's true. So you see the distance between here and there. Okay, that's gonna be your wavelength. Okay, so the wavelength, the unit is gonna be in meters, and then the time it takes at a given point to go crest, ho, crest is gonna be the period. Okay, so the speed of the wave, okay, it's going to be a distance over time. So it's going to be the wavelength divided by the period. And remember that 1 over the period is the frequency. Frequency means how many up and down in 1 second. So the speed of a wave equals to wavelength times frequency. Okay, so that's something that even if you take the MCAT, it's a very simple relationship. So for the same speed, if the frequency increases, the wavelength has to decrease. Is that clear? No? So I see some people doing something else. Are you paying attention, everyone? Right over there? She's paying attention. I cannot see. Are you with us? Hi? Yes? Okay. So you can do the same thing with light. Okay, so light is an electromagnetic wave, and if you are looking at the electric field, is also gonna shake. So crest to crest is gonna be the wavelength. At a given time, if it go up, down, up, it's gonna be the period. Now, do you see that as you move away from the source, it seems to be that they're going to be parallel to each other. Do you agree? Okay. And if you look at the strength, okay, as you move away from the source, you see the energy, the strength, okay, it's going to spread out over a large area. So it's going to decrease. It makes sense, right? Because the same energy here is going to spread out over a larger area. Okay, so we're going to see that as well. You can do the same thing with sound. You see, you have a sound wave. See that? If you increase the frequency, you see the wavelength is going to decrease, and then you lower the frequency. Again. Okay, so I have found on YouTube a very nice little YouTube video to review all the wave
is a disturbance which
Are you paying attention? So we review waves, right?
travels from one place to another, carrying energy, but without carrying material along with it.
So this here you have a slinky, and you see the coil of the slinky doesn't move from here to there. It's only the energy that is the disturbance, right? The energy that will be transported from one point to another one. You know that because if you place something here, it can kick you.
Many waves have a characteristic speed. The size and shape of the disturbance does not affect how fast it travels. This allows us to talk about the speed of sound, or the speed of light. The amplitude of a wave is how far from equilibrium it extends.
Okay, so from here to there, that's going to be the amplitude.
Harmonic waves, or sine waves, form a regular repeating pattern. The frequency of a harmonic wave corresponds to how many times each second a particular spot goes through its repeating cycle of motion.
Isn't that nice? You can really see it, right? So in 1 second, how many up and down it's going to go through, that will be the frequency. You see that point here does not move. Okay, so it's like if you are in the ocean and there are waves passing by you, you're going to go up, down, up, down. So how many up and down, up and down, up and down in 1 second? That's going to be the frequency. So it's a very nice way you can visualize. I like this video. So,
harmonic wave corresponds to how many times each second a particular spot goes through its repeating cycle of motion.
See, it stays here. How many up and
The
down?
corresponding wavelength is the distance over which the pattern repeats. The distance for the repeating pattern in space and the time for each cycle are related to each other through the wave velocity. The time it takes one full wavelength of the wave to pass a given point is the same as the time it takes that one point to go through one full cycle of its motion. Thus, for each harmonic wave, the product of the wavelength and the wave's frequency must be equal to the wave velocity. So a wave with longer wavelength must have a lower frequency.
You see that dot here doesn't
Shorter
move, right?
wavelengths have higher frequencies.
So it's a nice video to visualize what's happening. So if I go back to my electromagnetic spectrum, gamma rays have high frequency, unit is hertz, okay, but low wavelength. So you can think of the wavelength as the size of this wave, okay? So gamma rays will behave more like photons, little particles. And because their size are so small, it won't be stopped by your skin. So it will get through you. And it will be even smaller than a human cell. So it means when it's going through you, okay, if you're exposed to gamma rays, it will burp its energy inside your cell. So it will destroy the cells, right? So that's why gamma rays are used for PET scan, but you don't want to take too many PET scan per year because, of course, you are exposed to gamma rays. Then X-ray also have a small wavelength, okay, larger than those one, but small enough that it will get through your skin, but it will be stopped by the atoms of calcium, for example. And where do we find calcium? Bones, very good, right? So all the X-rays, they will go through your tissues, but it will be stopped. Most of them will be stopped, not all of them by your bones. That's why you will see a shadow. And then you have UV, UVA, UVB, UVC. Some of it will get to inside your skin a little bit, okay, and it can mess up DNA. So that's why our body has evolved to protect itself. So when we go outside, we tan. That's a way to be protected from the UV rays. And then visible light, of course, it's going to be safe. And then infrared, that will be heat wave. And as you go this way, you're going to increase the wavelength, decrease the frequency, and we're going to also see that you're going to decrease the energy. Okay, you have more energy carried by gamma rays that you have in radio waves. Is that clear? So in 1801, so Newton thought that light was made of particles of light. Okay, so for a long time, no one dared to contradict Newton because remember, he was not a super nice guy. He did not like to be contradicted. But then Thomas Young made a very famous experiment, okay, where he was able to show that light will behave like a wave. Okay, and then Einstein came later, 1905, and he said it can behave like a wave, but it also can behave like a particle. So it's like a particle wave. Okay, it has an identity crisis, right? So when light goes through space, it will behave like a wave, but when it's going to interact, like exposed to gamma rays, right? It's more like little projectiles, particles going through your body. It will behave like a particle. So that's why it's called a particle wave. Okay, so we'll talk about that. So anyway, in 1801, there was this very famous experiment done by Thomas Young that was showing that light behave like a wave. Okay, so I don't know if I have a picture. It's called double slit experiment, and definitively on the MCAT. So let's see if I have a picture of that. Double slit experiment here, you see, and it was to show that light will behave like a wave. So let me show you. It's always better to show you. Let's say you have water, okay? So you have two sources of water. They both have the same frequency. Can you see that the waves from the two sources are interfering with each other? Do you see that? So when you have crest and crest, what's going to happen? Big, right? They're going to be constructive interference. They will reinforce each other. Does it make sense? So here you have a big crest here and a big throw. So if you have a throw on top of a throw, it's going to be also constructive, right? You're going to have a big throw. But where you have a crest and a throw, what's happening here? So you have a bump and a down. What's going to happen? They're gonna, yes. So you have a up here, and then here you have a down. They're gonna cancel each other out. You're gonna have a flat. Do you understand? So here you have destructive interference. So that means a crest and a throw will be at the same time, at the same place, and they cancel each other. Isn't that beautiful? So if you're listening to music, for example, in a cheap concert, like something that doesn't cost a lot of money, and the sound is not very well organized, you're gonna have blind spot, right? You move a little bit, the sound is very, very high, and then you move this way, you don't hear anything. Because sound waves coming from two speakers, okay, they can reinforce each other or they can cancel each other. So there is this amazing demo, and why not? Maybe you can do it. Where is it? Amazing demo. You can do it on the pond here, okay? Maybe you can do that experiment.
Then the wave from one slit can interact with the waves from the other slit. I've got a demonstration here on a little pond where we can see this with water waves. I have two sources of ripples, which are basically like the two slits. When I create ripples with a single source, they travel out with circular wavefronts. Nothing particularly surprising there.
So you see here, crest to crest, that's going to be your wavelength, okay? And it's moving. Do you see how it's spreading away? Okay, so that's why the amplitude here is going to decrease as you move away from the source, okay? Because the same energy is going to spread out over a larger area. So anyway, it's a very nice
But
demo.
if I add a second source of ripples, then we start getting an interesting pattern.
Wow.
This pattern is created by the ripples from the two sources interacting with each other. Where they meet up peaks with peaks.
Look at that demo. If you could do that, you know, it doesn't cost too much because you have already a pond outside and it has to be very calm. And you need to shake it with the same frequency, okay? Otherwise it doesn't work. But you see here, along those lines, you're gonna have destructive interference, right? A crest and a throw kill each other out. So here you're gonna be safe, okay? It's all flat. It's not going to move. Isn't that interesting?
In troughs with troughs, the amplitude of the wave is increased. That's what we call constructive interference. But if the peak from one wave meets up with the trough from the other, then we get destructive interference and there's basically no wave there. And this is exactly what was happening with the light.
So Thomas Young, he did the same experiment but with light.
Light from one slit met up, peaks with peaks and troughs with troughs, they constructively interfered and produced a bright spot. But if the trough from the wave from one slit met up with the peak of the wave from the other slit, they would destructively interfere and you wouldn't see any light there.
So what he did, he has a source of light here, a source of light over there with the same frequency. So you have two, they will interact with each other, and here we'll see dark fringe, and here bright fringe. So that's I will show you another picture.
It's light canceling itself out.
This is basically the same as like having 2 drops of water fall in a swimming pool.
That's right.
Get exactly the same
And then they go and
pattern.
overlap. As this ripple overlaps with those ripples, down the bottom, you get a series of, you get like a bright spot. Sunlight, the reds are going to meet at different places than the blue. We're slightly colored. That's because the reds are going to meet up at different places.
That's what you get. Okay, so I will show you now with the app. So again, this is water. Do you agree? So what's happening along those lines here? Cancel each other. And the amazing thing, that was the experiment here done by Thomas Young. Okay, you can do it with light. So you have a source of light here. Okay, so it will be a laser, green laser. So same, you have a given frequency. And now you're gonna have 2 sources of light, so 2 slits. And look what's happening here. Along here, the light cancel each other. And if I put a graph, not a graph, a screen, you see here the light cancel each other. Here reinforce each other. Here cancel each other. Here reinforce each other. Isn't that amazing? So this is called interference, and that was the proof that light behaves like a wave. Okay, if I decrease the frequency, it's not going to be the same. Okay, so if I take blue, for example, on the screen, the pattern is going to change, but you see here, along here, light will cancel each other. Here, light will reinforce each other. So this is called interference. Okay? So this is called the Thomas Young experiment. Okay, so you take a laser and you have the laser going through 2 slits, like 2 small openings. So now you have 2 sources of light with the same frequency, and light coming from this source and light coming from that source is going to interfere with each other. If you have a screen, you're going to have a pattern here, bright, dark, bright, dark, bright, dark. Isn't that amazing? That light can cancel each other, right? So light can behave like a wave. So how can we make electromagnetic wave? So imagine here, do you remember the Van Graaff generator? Okay, so remember it's going to generate an electric field, so it's going to be a static electric field. What do you think is if for some reason I get mad at you and I take the Van Graaff generator and I start to shake it like this, right? What's going to happen to the electric field? Imagine this electric field here and you start to shake it. What's going to happen to the electric field? It's going to ripple. Very good. It's going to shake as well, right? So when the electric field starts to shake, it's going to induce a magnetic field. That will induce an electric field. That will induce a magnetic field, and so forth and so on. So that's how we make radio waves. Example, there is this great simulation. So here you are broadcasting something, okay? And here you are catching a signal. So this is called an antenna. And maybe you are playing a song at a given frequency. Okay, so in the antenna, electricity is going to flow up and down, up and down, up and down at the same frequency as your sound. And you're going to shake an electric field. So let's see if I oscillate. You see the electric field is going to shake. Okay, it's going to propagate. And here you're going to move. Because you remember an electric field will move a charge, right? So a charge inside your antenna, which is an electron, will also move at the same frequency. You see how it works? Okay, so this is how radio waves are produced. So an electromagnetic wave is made of a shaking electric field that will induce a shaking magnetic field that will induce a shaking electric field, and so forth and so on. Isn't that interesting? So you see that energy, it's energy that's being carried, okay, from here to there. And because the energy is radiating in 3 dimensions, of course, here you don't get as much amplitude. So you need some electronics here to amplify the signal. So if I do it in 3D, here, it looks more like this, okay, in reality. Okay, so this is an antenna. So in antenna, you have an electron that will shake, okay, that will produce an electric field. The electric field will shake, and the electromagnetic wave or the radio wave will move. Isn't that cool or what? Okay, it has to resonate here, okay? It has to shake at the same frequency here. So in 1865, you have Clerk Maxwell, that predicted the speed of light and how this electric field and magnetic field will behave. So here you have an antenna, okay? It's made of 2 wires, and you have some AC here, okay? So maybe it's going to produce AC at a given frequency. So you see the electric field here is also going to be produced. So you need an AC generator. So even if I take a magnet in my hand, when I start to shake the magnet, I'm going to make an electromagnetic wave. You don't see it with your eyes, but if you have an antenna close by, you will be able to pick it up. So if you take a magnet and you move the magnet like this, okay, you're going to have a shaking magnetic field that will induce a shaking electric field that will induce a shaking electric field, magnetic field, electric field, magnetic field, and so forth and so on. So they auto-generate themselves. So each time you have a wave, something has to shake. So if you take a slinky, you shake your slinky, so you have the coils that will be shaking. Let me ask you something. When I talk, I'm making what kind of waves? No. Sound waves. So what is shaking? Air, very good, right? Without air, there is no sound. It's the air that is shaking, and the energy is carried out until it's going to reach your eardrum. So it's going to shake your eardrum at the same frequency, and then a signal is sent to your brain, and you understand the sound. So in the case of an electromagnetic wave, okay, it can move into space. It doesn't need material. So what is shaking is the electric field and the magnetic field themselves. Okay, so you see here, if you have an antenna, okay, you see it's going to produce magnetic field that will be changing, that will induce an electric field that will be changing, that will induce ta-ta-ta, ta-ta-ta, and ta-ta-ta, and ta-ta-ta. You get it. Okay? So what is an electromagnetic wave? Okay, it has 2 components, an electric field that is changing and a magnetic field that is changing. Both of them are perpendicular to each other. So you take your right hand again, and there is a question on that on the final. So you have 3 vectors. You have the vector velocity, okay, so which way it's moving to. You have the vector electric field, and you have the vector magnetic field. So at a given point, okay, so if I stay at that point, you see the magnetic field is going to go in, out, in the screen, away from the screen, in the screen, away from the screen. At that point here, the electric field is going to go up and down, up and down, up and down, right? And the disturbance is moving in this direction. So you have to remember, very educated beaver. Very educated beaver. Very is for the velocity. Educated is for the electric field. Beaver is for the magnetic field. Okay? So you have one question like that because I just work on your funnel. Very educated beaver. Velocity, electric field, magnetic field. Now, of course, it's going to change with time, right? That electric field is going to go and oscillate in this direction, and the magnetic field is going to oscillate in this direction. But it's very educated beaver. And this is wrong here. I fixed it and it doesn't show here, but the magnetic field here is supposed to be in the screen. So I will fix it again, but the magnetic field is in the screen here. So for example, if you move here, very educated beaver. So this one is right, okay? Velocity is this way. Electric field is down. So magnetic field is in the screen, yes? But this one is wrong. The magnetic field should be towards you, okay? So very educated is up, magnetic field is towards you. So I fixed it, and I don't know why it didn't save, but here you should have dot. Is that clear? So very educated beaver. Don't ask me why, just. Okay, so I have found another nice video that summarizes everything.
Consider a light beam emitted by a source. It can be considered as a jet of particles called photons. Photons travel along straight paths at a very high speed. However, the light is also an electromagnetic wave. What does this mean? Well, it first means that at all points of the light beam there is an oscillating electric field.
So here you only see the electric field. So at that point, let's do very. Can you see here? We don't have too much resolution. You see the electric field is up, right? So very educated beaver. So the magnetic field is towards you. Okay? So the electric field is going to shake, okay, at a given frequency, the frequency of your electromagnetic wave. The magnetic field is going to shake at the same time. So when the electric field is large, the magnetic field is going to be large. When the electric field is zero, the magnetic field is zero. When the electric field is the opposite but large, it's also going to be the same for the magnetic field. The distance between crest and crest, that will be the wavelength, okay?
Which is inseparable from the photon jet. The plane of oscillation is perpendicular to the beam. Second, there is also an oscillating magnetic field. Its plane of oscillation is perpendicular to the light beam and to the electric field. Both fields are in phase. This means that if we focus on a specific point of the beam, they reach their maxima at the same time and cancel at the same time. The more intense the beam, the greater the amplitude of both fields. Now let's freeze the image at any time. The distance between two consecutive maxima or two consecutive minima is the wavelength of our beam. It is often represented with the symbol lambda, the Greek equivalent of our L. Different sources of light, whether or not visible, will normally emit electromagnetic waves with different wavelengths. Now focus on a specific point of the beam and observe the two fields defined at that point. Let's measure the time it takes for both fields to complete an oscillation. This time interval is the period of the electromagnetic wave. We call frequency the number of oscillations that the fields complete in a second. This definition implies that the frequency is the inverse of the period. It is represented as nu, the Greek n, and is measured in hertz. A hertz is an oscillation per second. Our light wave and the photons take a time t to travel a distance equal to the wavelength. Therefore, the speed of light is the quotient of both quantities.
Yeah, it's nice video, okay? Any question? So you see here, I have to fix this typo. The magnetic field should be going toward you, okay? So a very educated beaver. That's going to be here the speed of light. So it's finite, okay? So 3 times 10 to the 8 meter per second, or 186 million miles per second. So it goes really fast. Okay. Now, if you want to pick up an electromagnetic wave, like an antenna that you have in your phone, okay, you can have an antenna, or some of the car, you know, I mean, all the car, they have antenna as well. See, you have your antenna here, the electric field is going to come by. Okay, so the electrons here, it's going to shake because of the electric field. So in that circuit here, it's going to oscillate, and you can pick up the signal. Okay, you can do the same thing. Instead, you can have an antenna which is like a circle. So that way, you are not picking up the electric field, you are picking up the magnetic field. Magnetic field is going to oscillate, okay, through the loop. It's going to induce a current here, and that current here will be you go to some electronics and you turn that into electric signal. So that's how it works. So these are the equations of Maxwell's that will describe the behavior of static electric field, static magnetic field, changing magnetic field, and changing electric field. So this one you already know. It says that a static electric field always diverge away from a positive charge. So if you have a Van Graaff generator, it's going to generate a static electric field that will diverge away from the charge. If you have a negative charge, the electric field will converge. Okay? This one is just to say that you don't have a monopole. You never can find a magnetic charge. You always have a south pole and a north pole. You cannot have a monopole. This one is Faraday's law. It says if there is a changing magnetic field, okay, it will induce an electric field, or it will induce an EMF if there is a conductor. And this one says Ampere's law. It says that if a current is flowing in the wire, you're going to have a magnetic field circulating around. Okay? And it also says that a changing electric field can produce a changing magnetic field. So this is vector calculus, so you don't have to worry about it. Okay, so what's beautiful about those? So Maxwell wrote down those 4 equations, and then he started to play with them. And then you see here, you have 2 constants that you already work with. You have the magnetic constant and you have the electric constant. Do you remember those? Can you find these values? Do you remember the electric constant, epsilon 0? It was what? Minus 12, right? Something. And units. And then mu 0 is what? 4 pi times 10 to the negative 7. Very good. And Maxwell played with them, and then he did the following. Let's do 1 over the square root of epsilon 0 mu 0. Let me know what you get. Everyone is asleep today. I don't know what's going on. You're not the only one to fall asleep. Don't fall asleep. So do that. You know, I show you a way that can help you if you are taking whatever exam you are taking it. You start with the denominator, okay? So I'm going to do epsilon 0. So 8.85 times 10 to the negative 12. Enter, okay? I show you the trick. Times mu 0. So it's 4. Yes. 4 pi times 10 to the negative 7. Enter. Okay, and then you take the square root. So do square root, you call back the answer. Okay, so I did this, and then you take the reciprocal. Wow, what do you get? 1, 2, 3, 4, 5, 6, 7, 8. 3. So what is it? What is that number?
The speed of light.
The speed of light. So Maxwell, using these 4 equations, so they didn't know at the time that light will have a speed, and that will be the speed, right? And they didn't know about electromagnetic waves at the time. Just using those 4 equations, shaking them, massage them, all of a sudden come the speed of light. So he predicted electromagnetic waves, and he predicted the speed of electromagnetic waves just by playing with those equations. Okay, we talk about those equations, except we didn't do vector calculus, where we talk about electric field and magnetic field and so forth and so on. So everything is explained in 4 equations just by massaging, those 4 equations. He predicted the speed of light, and he predicted that light was actually an electromagnetic wave. Isn't that wonderful? And then later you have Henry Hertz, who did an experiment he was able to produce an electromagnetic wave and to detect an electromagnetic wave. Henry Hertz. He has a sad story because soon after he became very famous. I don't know what happened, but he died very young. So there was a story behind that, but I forgot. So isn't that amazing? So that will be the speed of light. So then you have experiment done. Okay, I'm not going to show you the video because I don't know, people tend to fall asleep today, but I will upload it in my in Canvas. Okay, that will show you how the speed of light was measured. But they did measure the speed of light, and guess what? Maxwell was right. And he got this value for the speed of light just massaging, malaxing, shaking those equations. Okay, so the speed of light is finite. It's big, but it's finite. So for example, you cannot have computers that are too large, right? Because the speed of light says that information will take about 1 billion seconds to go from here to there. So if you have a big computer, you do 2 plus 2, oh, it's 4, right? So even though the speed of light is big, it's a big number, nevertheless, it's finite. So it takes about 1 billionth of a second for light or information to go 1 foot. Okay? So when I look someone in the back, Kevin. You are Kevin? Okay. Kevin is far away, right? So it takes time for light coming from him to me. So do I see Kevin like he is now or like he was a few billionth of a second ago? A few billionths ago. Isn't that crazy? I cannot see Kevin as now. I always see him as he was a few billionth of a second ago. So if he was able to go really fast, I will not even find out because it will take time for me to find out that he's gone. Left the class. Okay? So when you look at the sun, okay, it takes 8 minutes for light, okay, to reach us, right? So I think there was one question also on the final like this. You have to use the equation speed is distance over time. So when you look at the sun, it takes 8 minutes for light to reach us. So do you see the sun as it is now or as it was 8 minutes ago? As it was, okay? So let's say the sun disappears, okay? It's abducted by some alien. How long do you have to live? 8 minutes. It will take 8 minutes, okay? So we still get light from the sun. 8 minutes, we're gone, right? We have 8 minutes to hug each other because otherwise, after that, it's going to be very cold, okay? So we have a unit for distance, which is called the light years, okay? So the Andromeda galaxy is 2.5 million light years away. It means it takes 2.5 million years for light from Andromeda galaxy to reach us. So do you see Andromeda galaxy like it is now or like it was 2.5 million years ago? Huh? Isn't that crazy? So if you have people or whatever, you know, strange beings observing us, they're not going to see us as we are now. They will see us as we were 2.5 million years ago. Right? So if you are 65 million years away, people will see the dinosaurs. Isn't that crazy? So if you look at the universe, okay, farther and farther and farther you look, back and back and back and back in time you go. So you can look at the universe just after the Big Bang. But after that we cannot see because light didn't escape the Big Bang. So we can see up to 300,000 years just after the Big Bang. Isn't that interesting? So it takes light, time for light to travel. Okay, so let's do some math. So you can wake up. So this is the electromagnetic wave. So that will be small wavelength, okay? And the wavelength is going to increase. For radio waves, it's going to be about 100 meter. So microwave, it's not micrometer, but it's centimeter. So microwave is that big. Visible light will be about 10 to the negative 6, so between 400 nanometer to 700 nanometer. And then you have X-ray and gamma ray. So let's try to do this one, okay? A microwave, okay, has a length of 10 centimeters. So that will be the wavelength. What is the frequency? So it's always the speed is the wavelength times the frequency, okay? The wavelength is in meter, the frequency is in hertz, but hertz means 1/second. Okay, so the speed is meter per second. Okay, so the speed of light is always 3 times 10 to the 8 equals wavelength times frequency. And you have to convert here 0.1. So you have 3 times to the 8 equals 0.1 times the frequency. So the frequency is going to be equals to, so you divide by 0.1, it's like you multiply by 10. So you're going to get 3 times 10 to the 10 or 9. 9, right? Because you divide by 0.1, so it's like you multiply by 10, okay? So you do 3 times 10 to the 8 divided by 0.1. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 hertz. Okay, so let's check here. Microwave, that's going to be, the wavelength is a few centimeters, and that's going to be the frequency. So a microwave is an electromagnetic wave. So the electric field here is going to shake 3 billion times a second. Okay, so that's crazy, crazy fast. Let's try to do this one, and let's try to see what is that. This one. So the frequency is 10 to the 12. What is the wavelength? So speed is frequency times wavelength. So 3 times 10 to the 8 is wavelength times 10 to the 12. So that's something very small, right? So you see, it's called misplaced base. So that means the base is 10. So because you divide, you're going to subtract the exponent, right? 10 to the negative? 4. Wait, yes, 4. So that will be about, in millimeter, can you turn that into a millimeter? 10 to the minus 3 millimeters is 1 millimeters. So that's going to be in millimeter, it's going to be 3 times 10 to the negative 1, right? Divide by 10 to the negative 3, right? So it's going to be 0.3. Is that right? Millimeters. So then you go back to your electromagnetic spectrum. Let's see if we can find what it is. So this is micro 0.3 millimeter. It's I think it's still a microwave. It's still a microwave here. Yeah, because this is 10 to negative 6, 5, 4, 3. Yes, I guess it's in the microwave still. Do you agree? You see how it works? Let's see if we have another example. What about this one? So the trick is, try to do this one, the UV one. You need to not forget how to convert. So nanometer means 10 to the negative 9 meters. Micrometers means 10 to the negative 6 meters. Millimeters means 10 to the negative 3 meters. Kilometers means 10 to the 3rd meters. Okay? So UV, the wavelength is 100 times 10 to the negative 9 meters. Okay, so the speed, it's going to be 10, that's here. So that's going to be negative minus 7 because it's a 2. Or you can plug into the calculator. So what you get? Three times 10 to the 15 hertz. So a UV, okay, so if you have an electric field in the UV electromagnetic wave, it's going to shake that much per second. So it's going to shake very, very, very quick. Okay, so if I was able to take a magnet in my hand and to shake it that fast, I will produce UV. Okay, if I take a vanguard arc generator in my hand and I start to shake it like crazy, I can produce UV, but of course it's impossible because it's so big. Because 100 times 10 to the negative 9. Because that means 10 to the 2. 10 to the 9. Okay? So that will be UV. Start to be bad. Any question? Okay, another video.
While electromagnetic waves are always transverse and in empty space, they always travel at the speed of light. But although they always have the same speed, they can have vastly different frequencies and wavelengths. And in doing so, these waves go so far as to create the entire electromagnetic spectrum. As a matter of fact, only when electromagnetic waves have a wavelength in the narrow range from 4 to 700 nanometers are the waves visible light. That is the spectrum from red to violet. Even shorter wavelengths, called ultraviolet light, are radiated by the sun. Though these invisible rays are dangerous to living things, they're absorbed and rendered harmless by the ozone in the Earth's atmosphere.
So you see how well the design is? We have ozone layer to protect us against UVC, for example, so it doesn't make it to the earth.
Shorter still are X-rays, with wavelengths the size of atoms.
So the size of the atom, so that means X-ray can be stopped if you have a big nucleus, like the calcium nucleus, right? So that's why you can see a shadow of your bones. And then you have X-ray.
And finally, gamma rays, with the shortest wavelengths of all. Gamma rays, with wavelengths as tiny as the atomic nucleus itself, are created by nuclear reactions. Longer wavelengths, extending to visible light and beyond, can be created or absorbed when atoms change from one energy state to another. Beyond visible light, there's infrared. With wavelength longer than red light, infrared radiation can be detected only by the heat it deposits. The universe is suffused with long wavelength radiation, seen as the cooled remnants of the Big Bang that started it all. That includes not only infrared radiation, but also microwaves. Microwaves are the first part of the spectrum, whose frequency is low enough to be generated by human-made, alternating current electronic circuits.
So microwave, like the microwave oven, right? So that will be produced by or radar, for example.
The universe is likewise full of radio waves. Centimeters, meters, or even kilometers in length, radio waves complete the electromagnetic spectrum. Of course, the great Michael Faraday didn't live to see the electromagnetic spectrum. Nevertheless, it began to take shape while electromagnetic...
Okay, isn't that interesting? I'm trying to do it in a nutshell. Okay, it's more complicated than that. Okay, let's do this one, but very quickly. Can you find the wavelength? So these are not radio waves, visible light. Just kidding, visible light. Okay, so that's the frequency of visible light. Let's just do this one. Find the wavelength. So that comes from your book again, the Johnson and Cudnell. So that will be the frequency. So the speed 3 times 10 to the 8 equals the wavelength, okay, distance crest to crest times the frequency. Okay, so with your TI, 3 times 10 to the 8, don't sleep. Yeah, 4 times 10 to the 14, make sure you close the parenthesis here, and you get 7.5 times 10 to the negative 9. 7. Thank you. Times 10 to the negative 7 meters. Can you convert in nanometers? Because usually visible light, the wavelength is in nanometer, okay? So 1 nanometer is 10 to the negative 9. Okay? Meters.
If you're going from big to small to nothing multiply, so that's what it's at. So -7 plus negative.
You divide. You divide because you want to know how many nanometers goes into here. You cross multiply, divide. So you divide. 1 nanometer is 10 to the negative 9 meters. So 7.5 times 10 to the negative 7 meter is what? Very good. Nanometers. Okay. And this is, I don't know if it's maybe blue. Do we have the blue and the, okay, the blue frequency? Okay, so 750 nanometer, and the smallest one is 380 nanometer. No, it's not blue. No. Which one has the largest wavelength? Red. No. Okay. Here you have violet here up to red. So which one has the smaller wavelength? Blue, okay, or violet, right? Because remember, UV is dangerous. Why is UV dangerous? Because it has a small wavelength. And if it has a small wavelength, it can get into your skin. So small wavelength will be blue, large wavelength will be red. Okay? So it means that this one should be like blue or purple. You can look it up online. And this one should be about red. Is that clear? So which one has the largest wavelength, red or blue? Red, okay? And blue, close to UV. UV is bad. It can get inside your skin. So small wavelength. Okay, so that's about blue, and that will be red. You can see that the wavelength, the range here is super extra small. So we are not super beings, because our eyes can only see this very small range of electromagnetic wave. We cannot see UV, we cannot see infrared. We can see infrared now with the night vision. Okay, the military people, they have those, or the firefighter, so you can see infrared. With telescopes, you can detect radio waves, UV, X-ray, and gamma ray. But we poor human, we can only see this. Like snakes, they detect infrared. That's how they can go after their prey. Mosquitoes, okay, or you can hide as much as you want under your cover, right? They will get you because they use infrared, so we are emitting heat, right? Okay, so I need to finish this part here because there will be one question for the final about that. But yes, we're gonna